I am Professor of Marine Technology at University College London and an international academician of the UK's Royal Academy of Engineering. In this video, I will share insights on oceanic solutions to address some of the world's grand challenges. Since the first industrial revolution, fossil fuels like coal, petroleum, and natural gas have powered the advancements in modern life. However, their extensive use has resulted in substantial carbon dioxide emissions, driving global warming and extreme weather phenomena such as storms, heavy rainfall, heat waves, and famines. Rising sea levels also threaten low-lying islands. Without urgent collaborative action, the continued degradation of our planet is inevitable. Addressing these challenges requires proactive international cooperation, as no single country can tackle them alone. The grand challenges we face today include global warming, energy and water shortages, food insecurity, health crisis, poverty, wars and terrorism, population issues, and more. The United Nations recognizes these challenges and emphasizes the role of the 14th Sustainable Development Goal, SDG, in leveraging oceanic solutions to address critical global issues. Covering 71% of the Earth's surface, the ocean is essential for regulating the climate and sustaining life on Earth. It is the backbone of trade, handling over 90% of the world's cargo. The ocean supports aquaculture and provides vast energy resources from surface wind and wave energy to oil, natural gas, and critical minerals beneath the seabed. Harnessing these resources is crucial for tackling pressing global challenges. The ocean presents immense opportunities to address these challenges, including cargo shipping, offshore energy generation, seafood farming, seawater desalination, and deep sea mining. Climate change, fueled by carbon dioxide emissions, is a critical issue. Oceanic solutions for achieving net zero emissions include zero-emission fuels for ship propulsion, marine carbon sequestration, and safe carbon storage in deep-sea reservoirs. These measures align with the global climate goals. Energy shortages are another pressing concern, worsened by the rising demand from technologies like AI and electric vehicles. Oceanic solutions include offshore oil and gas extraction and wind energy and wave energy harvesting. Clean water is a scarce resource for millions worldwide. Oceanic solutions for water shortages include seawater desalination and efficient water transportation to regions in need, providing a sustainable supply of fresh water. Hunger affects 1 in 7 people globally. Oceanic solutions for food security include efficient food shipping, sustainable seafood harvesting to protect the ecosystems, and responsible aquaculture to reduce pressure on wild fish stocks. Wars and terrorism pose significant threats to global stability. Ocean-based solutions include naval vessels for maritime security, submarines for intelligence and defense, and aircraft carriers and drones for rapid response and peacekeeping efforts. Innovations in ocean systems are key to meeting these demands. Examples include autonomous surface ships, advanced naval vessels, offshore wind turbines, floating power plants, seafood farming facilities, and seawater conversion systems. Oceanic strategies for shipping focus on environmental friendliness, cost effectiveness, and marine safety. Zero-emission technologies and alternative fuels help reduce greenhouse gases. Design innovations and improve the healthcare systems, lower maintenance and downtime costs. Proactive digital healthcare engineering systems enhance safety and sustainability in maritime operations. Although ocean activities contribute just 3.3% of global CO2 emissions, the International Maritime Organization, IMO, mandates zero emissions for all ocean-going vessels by 2050. Alternative fuels such as hydrogen, ammonia, methanol, and nuclear energy are being developed to meet IMO's targets. Among these, nuclear energy stands out for its high energy density and minimal greenhouse gas emissions, making it a viable option for achieving true zero emissions. Small modular reactors, SMRs, compact nuclear reactors with outputs below 300 megawatt offer promising solutions for shipping and offshore power generation. Their modular design enables cost effectiveness and operational efficiency. SMRs SMRs have been successfully deployed in over 400 naval vessels and floating power plants. With over 80 SMR types in development globally, these technologies are gaining acceptance and are projected to grow from 5.8 billion in 2023 to 6.5 billion by 2030. This slide highlights a 25,800 TEU container ship powered by SMRs, currently under development by my group at UCL. Here we present a Suezmax tanker-class ship-shaped nuclear power plant developed by my group at UCL. This innovation could revolutionize power generation for island nations, where land-based plants are impractical. The Russian floating nuclear power plant stationed at the Pevek, Chukotka demonstrates the feasibility of such solutions. Advancing safer, more sustainable oceans requires leveraging cutting-edge science and technology, especially in extreme conditions and accidents at sea. This includes the verification of safety performance through large-scale physical testing and refined computer simulations, together with the use of AI, Internet of Things, and advanced communication technologies. These videos showcase the world-class test facilities at the Korea Ship and Offshore Research Institute, KOSORI, and also highlights the advanced safety studies through refined computer simulations in extreme conditions and marine accidents.
UCL Marine Safety and DHE Group have been focusing on resolving safety issues in the maritime industry, including collisions, groundings, fires, and explosions. We are collaborating with the Korea Ship and Offshore Research Institute, KOSORI, to address these challenges. Various test facilities have been set up at KOSORI. This video introduces some of the physical testing and computer simulations conducted by UCL Marine Safety and DHE Group. This video demonstrates compressive buckling, collapse, and brittle fracture testing on a full-scale steel stiffened plate structure of a ship at -160 degrees Celsius, simulating a liquefied natural gas leak scenario. This video presents experimental and computational studies on collisions between icebergs and ship structures during Arctic operations. This video showcases structural crashworthiness simulations of a ship-to-ship collision accident conducted within the framework of collision risk assessment and management. This video showcases structural crashworthiness simulations of a ship grounding accident conducted within the framework of grounding risk assessment and management. These videos showcase gas dispersion and fire simulations on a ship-shaped offshore installation for oil and gas production in deep water, conducted within the framework of fire risk assessment and management. These videos showcase structural crashworthiness simulations of a ship-shaped offshore installation during explosions, conducted within the framework of explosion risk assessment and management. These videos showcase the structural crashworthiness simulations of a 25,800 TEU class container ship powered by small modular reactors during collisions. This video showcases structural crashworthiness simulations of a ship-shaped nuclear power plant during a terrorist attack involving a Boeing 777 airplane.
Digitalization and advanced communication technologies are vital for enhancing ocean system safety and sustainability. Low Earth orbit (LEO) satellites positioned closer to Earth than traditional geostationary satellites enable high-speed communication with a minimal delay. The next videos will demonstrate how LEO satellite technology is revolutionizing digitalization and communication in maritime operations.
What does the world look like beyond the color spectrum of the human eye? It can look like this, and like this, and this. It doesn't seem like much, but this is just a glimpse. The amount of activity that occurs outside the color spectrum is far greater than what occurs within it. It's like a parallel universe, except we don't have to travel beyond the stars to reach it. It is accessible right here, and we can call it data. Just as the eye captures data within the color spectrum, other devices capture data in the radio frequency spectrum. Radio signals that encode readable data like aircraft and sea vessel tracking, or signals that reflect off of surfaces like ocean wave height and soil moisture, or still others that bend from the density of the atmosphere to greatly improve weather forecasting and big weather events. Spire Global actually measures these bends at night and through clouds, providing unprecedented vertical weather profiles. Spire Global builds and operates the world's largest constellation of multifunctional satellites. Combined with our growing network of ground stations, Spire Sources collects, organizes, and analyzes data to help predict the future and fuel innovation. We have now reached a critical milestone in human history, where it is possible to construct a data-only replica of our home planet. Which begs the question, what can the world look like beyond the perspective of our self-imposed limits? It could empower you to help make changes like this. Or perhaps this. There is a parallel universe. It can be accessed, and it has been here all along. Spire, where the sky is not the limit, it's just the beginning.
In hostile ocean environments, aging ship hull structures face significant challenges due to age-related deterioration, including corrosion, fatigue cracking, and mechanical denting. The Digital Healthcare Engineering (DHE) system will be a game changer in managing these aging ships. The DHE system consists of 5 key modules. The first module is on-site health parameter monitoring. Through this module, health parameters, such as wave profile, in-service damage, and operational conditions, will be measured on board. The second module is health data transmission via LEO satellites. The measured health parameters will be transmitted to a land-based data analytics center using low Earth orbit satellites like Starlink. The third module is data analytics and simulations with digital twins. In this module, the transmitted health data will be analyzed for computer simulations. Based on the analyzed health data, real-time health conditions will be assessed using computational fluid dynamics and the nonlinear finite element method. The fourth module is AI-driven diagnosis and remedial action recommendations. In this module, structural defects are detected and proper remedial actions are recommended by AI. The final module is predictive analysis for future maintenance planning. Based on the accumulated health data, the DHE system will enable the prediction of future health conditions. The predicted data will be instrumental in planning future maintenance schemes. By integrating all the key modules, the DHE system functions as a cohesive unit in real time. Our research group is currently developing not only ship DHE systems, but also DHE systems for other marine structures. These include monopile type, jacket type, and floating type offshore wind turbines, offshore jacket platforms, ship-shaped offshore installations, nearshore LNG storage tanks, and even DHE systems for seafarers.
Thank you very much for watching.